Welcome to this calculus based physics lecture on electric potential and electric potential energy. In this comprehensive session, we will explore foundational concepts in electrostatics from work and energy to dipoles, fields, and real world applications like printers and particle accelerators. So let's begin. When a charge moves in an electric field, the field can do work on it, just like gravity does when an object falls. In this diagram, you have an electric field set up between two oppositely charged parallel plates. The field is from the positive plate to the negative plate as shown in the diagram. Consider that there is a positively charged particle which is kept near the positive plate. Because of the influence of the field, the positive particle will move towards the negative plate in the direction of the field. That means work is being done by the field in this case. This is exactly like an object kept at a height because of the gravitational field falls to the ground, in which case gravitational field is doing work on the mass. Now, coming back to this example, the work done by an electric field is defined as the line integral of the force over displacement. The line integral, that means you have to integrate over the path taken. And in this case, the force is QE, as we have seen in the previous chapter. And work always involves change in potential energy. And this formula shows that when work is done by the field, the potential energy decreases, as shown by the negative sign. On the other hand, if this was a negative particle and the negative particle was on the positive plate here, now the field cannot move it towards the negative plate. Instead, an external force must be applied to move that negative charge particle to the negative plate. That is just like lifting an object to a height from the ground. Therefore, in this case, the potential energy increases. Now, so the definition of the work done gives us a direct way to relate electrical forces to energy. Here's an example. A proton moves from point A to B through a uniform electric field of 100 Newton per Coulomb over a distance of 0.05 meter. Calculate the work done. Work is Fe times d. Now, in this case, we're not using the integral, and you see the dot product vanishes because theta is 0 and cosine 0 is 1. So you just take the product of Fe with d. And since we know the charge of the proton, we know the field given, we know the distance, you get the answer in joules. As you can see, the units Coulomb cancel out here, and then you have Newton times meter, which is a joule. We've already spoken about electrical potential energy. Now, it is the energy stored due to the position of a charge in an electric field. And in a uniform electric field, the formula for potential energy is charge multiplied by the potential. Now we know that we can use another formula for this, which we will do later. I just want to give a hint here voltage could also be written as E times D. So that could also be a method of calculating the electric potential or voltage. So here's an example. What is the electrical potential energy of a 3 microcoulomb charge at a point where the potential is 12 volt? All right, you're given the charge and the potential, 3 microcoulomb here, and you have 12 volts, so you get the answer in joules. So that's electrical potential energy. But we also need to consider the total energy. For example, when we go back to this electric field, and if we started with a positive charge near the positive plate, we know that the field will accelerate the positive particle towards the negative plate. That means it starts with a zero velocity, its kinetic energy is zero, but as it moves through the field, it accelerates, its velocity increases, and by the time it gets to the negative plate, it's moving fast. And at that point, it has a lot of kinetic energy. So you have to consider both the potential energy and the kinetic energy. Remember, we did say that for a positive charge, as it moves to the negative plate, the potential energy decreases. But at the same time, its kinetic energy increases. Don't you see the similarity with a gravitational field, where if you have a mass at a height at rest and you drop it, as it starts falling, its potential energy, gravitational potential energy in this case, is decreasing, but its kinetic energy is increasing. So it's a perfect example, as you can see shown here. But at any point in the field, if you take the total energy, you will find that they are the same. What is this called? This is called the conservation of mechanical energy. So the conservation of mechanical energy applies, and the sum of the kinetic and the potential energy is always equal at any point. So here is another worked out example. How much work is required to bring a 1 microcoulomb charge from infinity to a point 0.2 meter from a 2 microcoulomb charge? So you start from very far away and you're bringing this 1 microcoulomb and situating it 0.2 meter away from a 2 microcoulomb charge. So the 2 microcoulomb is here, and you're bringing the 1 microcoulomb from very far off, and then you're ending it there. So this distance is 0.2 meter. So that's the picture. And in this case, because work is actually the change in potential energy, so I got to write change in potential energy here. And at infinity, the potential energy is taken as zero. Just like in gravitational fields, the gravitational potential energy at the ground is taken as zero, same way. And therefore, the change in potential energy is just the potential energy, see, because we started from zero. And then it is the charge multiplied by, that's the charge we are bringing, and this is the potential due to that situated charge. So Q1 is here, and you're bringing Q2. So there is the potential for this field, and then you bring the other charge into the field. So when you see that formula, now you understand where it comes from, and now plug in the numbers. Remember, both of them are in micro. That's why there's 10 to the negative 6. And then you get the answer. We have now looked at electric potential. We've looked at work, electric potential. There's another thing called potential difference. And We also call it voltage. Voltage is just another term for electric potential. But you have to understand the relation between electric potential and potential energy. Look at these terms. They're not the same. To get electric potential, all you have to do is divide the potential energy by the charge. So that's the formula, very important one. So electric potential is the electric potential energy per unit charge. So once again, the unit is very clear now. The unit of potential energy is joule and charge is in coulomb. So the unit of electric potential is joule per coulomb. And this is also called a volt. And then when we talk about potential difference, we are talking about the difference in potential between 2 points. So if V sub B is the potential at B, V sub A, that at A, the difference between them is given simply by the negative, notice that, the negative line integral A to B of E dot dr. That's going to be a very important one to work out problems. So a 5 microcoulomb charge has 0.015 joules of potential energy. So when it's at a point, that charge has that much potential energy. What's the electric potential? Very simple. You just divide its potential energy by the charge, and you get 3000 volt. Or you could have it this way. Find the potential difference across 2 points separated by 0.04 meter in a uniform field of 250 Newton per coulomb. Well, let's go to this example. So let's say that these two plates are separated by 0.04 meter, and we know there's a field here in that direction. Let's say that field is 250 Newton per coulomb. So you have that field and you have the distance. And this is where I reminded you that there is another formula that we could use. This is where you're going to use that formula to get, oh, where's that? Okay, to get that potential difference is negative E times D, which comes directly from here. Look at that. Negative E times the dr is now replaced with D because that's a uniform field. The integral is required only when the field changes. So if it's a uniform electric field, you have a much simplified relation. Okay, so 250 is the electric field, the distance given, so you can calculate the electric potential. All right, now I want you to be introduced to a new unit of energy, which is basically used in the atomic system in the microscopic world. Because when you deal with particles in the subatomic world, the joule is a pretty big unit. Okay. So that'll be like trying to measure the thickness of paper in kilometers. The kilometer is too big to represent the thickness of paper, so you'll have to have a very small number. Same thing. That's why the electron volt has been introduced. And what is the electron volt? I'm glad you asked. It is the energy gained or lost by an electron when it moves through a potential difference of 1 volt. So if the potential difference between these two plates was 1 volt and you were moving an electron, let's say from here to here, you would have to do 1 electron volt of work. So the energy gained is 1 electron volt. What about if you had if you had a potential of 2 volt? Well, then you would have to do more work, and the energy gained would be 2 electron volt. Okay? So it's easy. If you're given the voltage, like I've shown here, an electron is accelerated through a potential difference of what? 500 volt. How much energy does it gain? 500 electron volt. There. You could straight away do that. Whatever is the voltage through which an electron is accelerated, that is how much energy it will gain in electron volts. See, that even makes it simpler. But if you want to change electron volt to joules, then you have to use this. And this is the charge of the electron. So 1.6 times 10 to the negative 19 joules is 1 electron volt. All right, before we move on, I just wanted to highlight a very important difference between electric field and electric potential. Now, first, we've seen that electric potential, change in potential or potential difference is given by this, or we've already looked at this. Voltage is negative line integral E dot dr. Now, you can write it backwards, which means the electric field is negative dV by dr, because integration and differentiation are opposite functions. All right. So remember that these two formulas can be interchangeably used. But the difference that I wanted to highlight is that electric potential is scalar, while electric field is vector. You will never see this done for electric potential because it's a vector. Ah, what did I say? Sorry. Because electric potential is a scalar, while electric field is a vector. Now we'll come to this diagram later on, but I just wanted to tell you that this is the representation of both the electric field and electric potential by a point charge. The red lines give the direction of the electric field, or that it represents the electric field, while the black ones show what's called equipotential surfaces. We'll get to that in a minute. But having introduced the electron volt, I wanted you to know that the context of use of the electron volt is spread across a lot of fields. For example, in atomic physics, energy levels of electrons are typically in electron volt. Now, I think the first orbit energy of hydrogen is negative 13.6 electron volt. And then the second orbit is something like negative 5 point. I can't remember it exactly. I just want to say that it's all expressed in electron volt. Nuclear physics, and there the binding energy between the neutron and the proton inside the nucleus is expressed in mega electron volt. You may wonder why. It's because those energies are really big. That's why an atom bomb produces a lot of energy, because you're getting the energy trapped inside the nucleus. And this is a simple example which you've already done. So to convert electron volt into joules, just multiply with that number, right? Okay. Conservation of energy, we've already done that, but I wanted you to take a closer look at this diagram. The negative plate, or anything that's negative, is taken to be at 0 volt. See, the negative plate is taken to be at 0 volt. Now, this is just like taking gravitational potential energy at ground as zero. Because we are only interested in the change, not in the actual value. And if there is a battery connected between these two plates, and that can provide 100 volt, then the positive plate is at 100 volt. And so you can see that you have a potential gradient, which means as you go from 100, as you go from the positive plate to the negative plate, the potential steadily decreases. But if you look at this line, at any point on this line, the potential is 75 volt. See? That's why it's called an equipotential surface. An equipotential surface. Potential is equal. Similarly, here it's 50 volt. This is the equipotential for 25 volt. And one thing must be very clear, that the electric field is always perpendicular to an equipotential surface. Always perpendicular in any case. You can see that towards the end of the plates, the electric field is distorted, and so is the equipotential to make itself always at right angles. That's a very important thing. And this problem also illustrates that the potential difference can also be calculated by the change in kinetic energy by Q. Earlier, we had seen that it's a delta U by Q or U by Q, which is potential energy by charge, but it can also be kinetic energy by charge. That's what that question shows. So if an electron gains that much energy, you want to find the potential difference, just divide the energy by its charge, and you know it's 2 volt. Okay. Now, before I move on, I just wanted to ask you, if this was taken to be at 50 volt, this would be at negative 50 volt. See that? Once again, that makes the potential difference what? 100 volt. Now, we don't want to do that because that's technically harder to visualize. That's why we took the negative plate to be at 0. And that is the general trend in electrical circuits. So how does the potential due to a point charge look like? We already looked at this diagram and I did explain. Now you know that these are equipotential surfaces. And since it is a positive charge, the potential, as you go away, look at that, the potential is decreasing. As the distance increases, the potential decreases. So we have a very important formula. The potential due to a point charge is K Q by R. All right, so if R is equal to infinity, what happens? If R is equal to infinity, then voltage is 0. Anything divided by infinite gives you nothing, which means that at infinity, potential due to the charge is positive. I mean, it's 0. So as you come closer, the potential increases. Make sense? But at every point, the potential is positive, no? Because it's a positive charge. On the other hand, if it was an isolated negative charge, then at every point, the potential is taken as negative. Once again, the potential at infinity is 0, even in this case, but it would be something like negative 10 here, negative 20 here, you see? It's again increasing in magnitude, just like for a positive charge. Or I think this example should make sense. What is the electric potential? 0.5 meter away from this charge. All you got to do is K Q by R. Micro, that's why there is 10 to the negative 6. That's the answer. And look at that. That was a positive charge. What if it was a negative charge? If it is a negative charge, you have to put negative in the formula. See that? And then you end up with a negative voltage. So that's a new formula that's important. K Q over R is the potential due to a point charge. What if you had a lot of charges? Like you had Q1, you had Q2, you had Q3, and so many charges. Not necessarily in a straight line, but it could be all around. And what if you wanted to find the potential due to all of them at this point? Okay, you know, it's easy because potential is a scalar. we can just calculate the potential due to each individual charge at that point and then sum them up. Take the vector sum. So electric potential is a scalar, so the total potential at any point due to multiple charges is the algebraic sum. Now that word means, remember, if it's a positive charge, it should be positive. If it's a negative charge, then potential is going to be negative. That's what the word means. And that's how it's written. The summation of all the I particles, K Q sub I by R sub I, where R sub I is the distance from the point to the ith charge. Here's an example. That's the diagram that I've drawn. You have two charges, Q1 and Q2. The charges are given, and their distances from the origin are given. Find the total potential at the origin. Well, you see KQ by R. Okay, the K, part of the K is there. KQ by R plus KQ by R. Of course, the K is taken out. All right. But did you notice this? Because one of the charges is negative, remember to use negative. And then do the math, you get the answer. All right. Electric dipole, we have used it in we have looked at an electric dipole before. We know it consists of two equal and opposite charges separated by a small distance. Now, the potential field that it sets up is unique. And there are two formulas that I want you to know. One is the potential on the axial line. So if you had the dipole like that, and you were looking at electric potential on this line, that's called the axial line. Then you could use this formula that's given here, K P by R squared. Now that's just a unit vector showing the direction. So it's K P. Do you remember P? P is called the dipole moment, which is what? Q times D. Q is one of the charges, D is the distance between them. So if you know the dipole moment, all you have to do is K times the dipole moment by R squared. And that's what the example shows. Given a dipole with charges plus minus 2 microcoulomb, remember both have to be equal, except that one is positive, the other is negative. And they're separated by a short distance, 1 centimeter. Find the potential at a point 20 centimeter along the axis. You see that? Along the axis. So the formula only works if the point is along the axis. All right, K, that's K. P, see that? Dipole moment. Q times D, but this has to be in meter, so that's why it's 0.01 meter. At a point 20 centimeter, once again in meter square. And you get the answer. That is an electric dipole. What about instead of having charges, many charges, multiple charges like that? What about if it's a continuous distribution of charges? Like you have a cable which is continuously and uniformly charged. See that like that? So there are charges all over it, uniformly spread out. In that case, instead of the summation, we have to use integration. So the idea is the same. We take the potential due to all of the charges, and integration is replacing summation. Right? When we apply the calculus and derive the formula, which I'm not doing, being an online course, and again, this video would then go into multiple hours, I want you to know this formula. This is the potential at a point on the axis of a uniformly charged ring of radius r and total charge q. So the diagram is given. So you have charges all over this ring, and you want to find out the potential at a certain point P, which is, well, in the formula, it's given by X, in the diagram, it's Z. I hope you forgive me for that. Okay, so R is the radius of the ring, Z or X is the distance of the point from the center, Q is the charge on it. Okay, so you got three quantities, and here's an example that's I mean, so that's the formula you would use. I've not given any numbers. If it were given, you just substitute and work it out. But the second example talks about a line of charge with linear charge density lambda, where you have charges now spread out on a cable, like I said before. In this particular case, the formula becomes lambda by 4 pi epsilon naught natural log d by d minus L. Okay, now you know that d is the distance from the center of that line charge where we want to find its potential, and L is the length of that line charge. Lambda, you may recognize, is the linear charge density. What's that? That is Q over the length, total charge over the length. So that's lambda. So first, if you're given the charge, you're given the length, first you'll have to divide and find lambda. Once you get lambda, you got D, where you want the field and the length, plug it into the formula, and you will get the answer if you do it carefully. Okay, so we come to another very important part. Here, the relation between electric field and potential, we've already looked at it. But I just remember, do you remember this? E is equal to minus dV over dr, yeah? But if it's in space, then you could write it as E is equal to minus di V. That's how you read it, divergence of voltage. Well, in Cartesian coordinates, this is what it means. The electric field in the x direction is minus dou V by dou x. In the y direction, likewise minus dou V by dou y, and the z direction. The example should make it clear. So if you are given a voltage as a function, 5x squared, and you're asked to find the electric field along the x-axis, all you got to do is minus dv by dx, use calculus, and you get minus 10x, right? 5 times 2, 10x. What is minus dv by dy in this case? 0. That means there's no electric field in the y and similarly in the z directions. Okay, look at example 2. Now you have a 2D potential. This is 1D. So now voltage is a function of both x and y, and that's why you have 3xy. Now this is going to be important for the exam. So find the electric field vector. Now you've got field along both the x, which is minus 3y. You know that. You're going to get 3y because you are doing it with x. You're taking the differentiation with x. So if you do it with y, then y vanishes and you get minus 3x. Therefore, in vector form, the field is given by minus 3y I cap minus 3x j cap. You know that these are the unit vectors on the x and the y axis, don't you? All right, so we're coming towards the end of this chapter, but here's another example, exactly what I've been telling you. The electric field component in a specific direction is the negative partial derivative of the potential with respect to that coordinate direction. We looked at that. It's written here. And if you're given a function, now this is a repeat, so I'm going fast, and you're asked to find E sub y, then you got to do negative dou v by dou y, which will give you simply -3, because this whole thing becomes 0, -3. What does that mean? That means the potential is constant. It's not changing with y. Or another example, if it's a 1 over r in spherical coordinates, and then you calculate E sub r, you know spherical coordinates, r and theta. So you just take minus dv by dr in that case, and you get negative 1 by r squared, which is 1 by r is 1, 2xy, 10xy. I think we did something similar to this. E is -10yi plus 10xj. I think that is the end of this chapter, but we talked about equipotential surfaces and equipotential lines, but I just wanted to summarize. An equipotential surface is a 3D surface on which the electric potential is the same everywhere. Now, in diagrams, you only show 2D, but it's actually 3D. Key properties: no work is required to move a charge along equipotential. Why? Because by the definition of potential, if the potential at 2 points is the same, like this point, the potential is the same, what's the work required to move any charge between them? 0. And electric field lines are always perpendicular to equipotential lines. Now, I already said that. And then the closer the lines, the stronger the field. Yeah, if you draw the lines very close to each other, means it's a strong field. If you draw them further away, that's a weaker field. Yeah. All right. So we looked at this again. Know that the black lines show the equipotential surfaces around the point charge, while the red lines give the electric field, and they are always perpendicular to each other. So electric field lines always point in the direction of decreasing potential. Yes. Remember that? Because for a positive charge, it goes from here, it's decreasing, the potential decreases to 0 at infinity. Well, by the by, you also have the electric field and equipotentials due to two opposite charges, as shown in the diagram here. You just need to be able to recognize them. Okay, so now here's the question. If two equipotential lines are spaced 0.02 meter apart and the potential difference is 10 volt, what is the field? Oh, you just divide them, because we know it's a change in potential by distance, z. We've done that so many times. Maybe you wrote it as this is E times D, same thing, right? Okay. Now, electric field lines can never intersect equipotential lines at an angle other than 90 degrees. Why? They are always perpendicular. Why? Because if there was any component along the equipotential direction, then work would have to be done taking it on the equipotential, which is impossible. So, to summarize, the entire conductor is an equipotential. If you have a sphere, a metal sphere charged, the entire surface is equipotential. We know there's no electric field inside. We also know that an excess charge always resides on the surface. Now, there are many applications of electrostatics. I want you to just look at those, without thinking that this was completely a conceptual chapter. Laser printers and copiers, we use them on a daily basis. They use electrostatic charges to attract tonal particles to specific locations on paper. So that means that paper is charged, and then the tonal particles stick to the paper depending on where the charge is. This is the same in inkjet printing. Electrostatic forces, direct charged ink droplets. In this case, it's not the paper, the ink droplets are charged and they are put in precise positions. Now, to remove particles from air purifiers use the same idea, because it charges the dust and then attracts them. collecting them on oppositely charged plates. Paint sprayers, you may have heard of uh, electrostatic paint sprayers where paint is distributed evenly. Okay, so there are so many uh, applications. How does a laser printer utilize electric fields? You know, there's a drum in a laser printer, which is electrostatically charged, that charges the paper, and then you can discharge the drum selectively to form an image as you send from the computer. So only those places. So if it's a big A that you want to print on the drum, corresponding to that A, the charge is removed selectively, and therefore toner particles stick only to those discharged regions. Okay. All right. So that is this chapter. And I know I'm going really fast because I want to make the time for the video as small as possible. And I know that you can always pause and listen, but please consider this to be the lecture, and it's in place of you reading the whole text. So listen to it maybe a couple of times, watch it, make sure you understand the concepts. We'll see you on the next one. Thank